Okay, so we talk about time memory trade-off cryptanalysis. It is a generic attack on any inverting to invert a one way function. So, that one way function. So, what is a one way function? One way function is basically if we have a mapping from A to B, this is A set, this is B set. So, from this way it is easy. If we have a x, it is f of x, which is basically y. So, this is easy, means there is a polynomial time algorithm to compute this, and but this is hard, this way it is hard. So, given a f x or y, it is hard to get x is called. So, that is basically inverting f is called one way function. So, we will see how the cryptographic primitives like block cipher, stream cipher and other primitives also can be viewed as a one way function. So, attack on this basically attack on block cipher is basically inverting such a one way function. Okay. So, slide please. So, this is the one way function. So, one way function, can you go to the slide please? So, here we have a x, we can easily compute f of x, and from f of x it is hard to get x. So, this is the one way function. Now, we will see how we can have this one way function from block cipher or stream cipher. So, basically a block cipher is a function which is taking n bit plain text and giving us n bit ciphertext, and s is the key size. So, each key is a s bit. So, this is the key space. So, E is a function from plain text space cross key space to the ciphertext space, and P is the plain text and C is the ciphertext and key is the key. This is denoted by E K P. Okay. So, if we fix P, then we define, if we fix P, then this is basically a function from key space to the ciphertext space. So, this is basically E, which is basically plain text space, key space to the ciphertext. So, if we fix a, so this is the plain text space, this is the key space, this is the ciphertext space. So, if we fix a P, and then it is basically E P we can denote. So, this is a function from key space to the ciphertext space. Okay. But this function is basically from s bit to n bit, but we want this function to be s bit to s bit. So, and this function is a one way function, because if we have a ciphertext, this is a non plain text attack. If we have a ciphertext, now if we can get the corresponding key, then that is the attack on block cipher. Okay. So, but now we want this to be same. If it is, if s is equal to n, then no problem, but if it is s is not equal to n, say for example, for ds this is 64, this is 56. So, what we can do to make this s, we can reduce some bit, we can remove some bit. Okay. And for AES, this is 128 bit, and if it is 128 bit, but the AES has many version of key. If it is more, then we can add some of the bits. So, this is the way we can have this. We can have a R on this after this to make it s bit to s bit. So, this f is basically is the one way function we are looking for. Now, the challenge is to invert this x f. So, the challenge is to, this is the non plain text attack, we have a plain text and we have the ciphertext. Now, the challenge is to invert that f to get the key. So, because now the function is from key space to the ciphertext space. Why we need the same domain and codomain? Because we want to apply f repeatedly for our time memory trade-off attack to have a chain. We keep on apply f. Okay. Now, this is the way we look block cipher as a one way function. Now, we look at stream cipher, how we can look at stream cipher as a one way function. So, this is the general structure of a stream cipher. So, in stream cipher what we have a state, it could be LFSR based stream cipher or any general stream cipher. So, it is basically a finite state machine. We have a state which is basically sometimes it is initialized by the key, or we initialize this by the IV initial vector, and we run this state few times, the initialization process, and then we get a initial state, and then we have a with the key and IV, that is called initialization vector, and then each time, each clocking, the state is updating by the g function. It is taking the value of the state, and it is output is giving the next state values, and for the key stream what we have, it is taking the value of the state at that point of time, it is applying a f function, and it is generating the key stream. Depending on how many keys we need, we will keep on run this, and then that key stream is XOR with the plain text to get the ciphertext bit. So, this is a general synchronized stream cipher, because here the plain texts are not involved in this business, in this part, plain text neither ciphertext. So, this is only coming out to be. So, this is the synchronized stream cipher. There is asynchronous stream cipher where this plain texts are also can be participate in the this state updation function. Okay. Now, how we can have a one way function out of this? So, we just defined a function f from the state space. So, this is the set of all possible state space to this. Now, if the state is say s bit LFSR for example, you can say, okay, then this function we define the first s bit key stream. Okay. Now, just first s bit key stream. Now, this is key and IV from the key stream. So, this is a one way function, because if we know if we could invert this, then we will be knowing the initial we'll be knowing the some value of the internal state. Once we know some value of the internal state, then we can get all the key stream, forward key stream. We are running the state, if we know some value of the internal state at some point of time, then that value will be creating this key stream in future. So, all the key stream will be known on that onwards. So, this is the attack on the stream cipher. Okay. So, other modes or other primitives are also can be think as a one way function. So, basically our problem is to invert a one way function. So, our problem is we have a function f s bit to s bit, and this is a one way function. This can either derive from block cipher or stream cipher or modes of operation, and the challenge is to invert this one way function. So, given a y which is basically f of x, how to, the challenge is to get, need to invert, need to get x. So, how to get x? So, that is the problem definition. Okay. So, this is the problem definition. Given a y from this f of x, we need to invert this. So, this is we can do in generic way. So, like we have seen the exhaustive search attack, which is basically brute force method, which will try for all possible key. Now, to resist against the exhaustive search attack, depend on the size of the key space. If the key space is more, it is not possible to do the exhaustive search attack. Then one can think of parallel processing. Even with the parallel processing also, if the size is very big, like for AES, it is the size of the key stream is 128. So, it is 2 to the power 128. So, even if we have say 50 processor running in parallel, so then also 2 to the power 128 is the time. So, 2 to the power, say if we have 56 also processor, then it is 2 to the power 70, which is huge. So, exhaustive search will not work on this AES, but we have seen on DES key size is 56 bit, and if we have 36 machine running in parallel, this is the attack done by Electronics Foundation. They made a hardware to attack this, and this is basically 2 to the power 20. So, this can be achieved. So, it depends on the size of the key space, where if the key space is less, we can have a special purpose software hardware to have this. So, like I said, Electronics Foundation, they build a machine, parallel machine with this. Now, this attack cannot be mounted for multiple targets. Suppose we have many x, y1, y2, yd, then every time we have to run this. So, how to handle this multiple target? So, for that Hellman introduced this time memory trade-off attack on 1980, and basically it consists of two phase. One is pre-computation phase, which is we call offline phase, another is online phase, and then later on reversed, modified this using the distinguish point, and then later on some work by even we have some contribution in this area. So, let us talk about Hellman method. So, Hellman method on. So, you can write TMTO, time memory trade-off attack. To invert a one way function. So, we have a y. So, what it is doing? It has two phase, offline phase and online phase. So, in the online phase, so earlier we have seen we are doing that table lookup method. Table lookup method means we are storing this basically. So, we have to invert this f. So, we have given y is equal to f of x, we need to get this y. So, in the table lookup method, what we are doing? We are choosing a x1 and we are getting y1, which is basically f of x1 like this. So, we are storing for all possible xn. If so, it is basically f is basically 0 1 s to 0 1 s. So, basically we have n is 2 to the power s. So, 2 to the power s possible values we have. So, then yn f x n. So, basically we are storing these two pair in an increasing order of the endpoint, and this is also two phase. This is offline phase or the pre-computation phase, and in the online phase what we do? We have given a y, which is basically f of x. We do not know x, we need to find x. So, what we do is search for this y in the endpoint, and if we got say yk, if yk is matching with this, then the corresponding xk is the key. So, just a table lookup will give us the solution, but the problem is here we need to store all the values over here. So, if n is large, that could be expensive, that many memory we may not be having. Also the memory access time. So, where we are keeping this data, where we are keeping this table in the CD, in a hard disk, that time also should be considered into the run time, because if we are keeping this in a RAM, okay, then it will be faster than if we are accessing the hard disk. So, that time also should be considered. Now, here time memory trade-off means, okay, so here we are online time is less, but memory is more. So, somehow if we can trade off these two, time and memory, we have some memory, not very much, and we have some, we can spend some time at the online. So, there is a trade off. So, that is the idea of Hellman. So, what Hellman did? Hellman compute some Hellman compute a table like this. So, Hellman choose some points, say 2 1 3 1, these are called start point. So, Hellman choose randomly m points from the, say these are all s bit. So, we are looking our f is s bit to s bit. Okay. So, Hellman choose some, these are all s bit number, and then Hellman compute a chain, apply f on it. So, it will give a also s bit number. So, this is basically S12, again apply f on it. So, S13 like this. So, continue like up to S12. 1 t. Okay. So, this is a chain. So, if we have this x, so for ith row, so if we have say x I 1, if we apply f on it, this is, so this is basically f of x I 1, which is again we are going to, so this is again a s bit. So, if that is why we need the domain codomain should be same, because we want to repeatedly apply f on these numbers. So, that is the reason we want to make it same domain codomain. So, again we apply f on it. So, we got f I 3. So, which is basically same as f of I 2, which is basically f of I 2 like this. Okay. So, this way we will continue. So, after we got, so this is f of I t minus 1 and we got, so f of I t minus 1 is basically f of I 1 like this. So, this is basically f of I t. So, f of I t is nothing but f t times on this f of I 1. Okay. So, this is the Hellman table. So, here is the Hellman table. So, we choose the start points, like it is starting from 0, 1 0 like this. Anyway, we have taken from 1. So, these are the start point Hellman is choosing at random, and then compute this f on each of these, and again it is a s bit, again we can apply f on it. So, like this we are continuing and we are ending to a end point x 1 t. So, like this we are doing, and then x 1 3 0 x 3 1 like this we continue like this. So, this is we are doing in people offline phase, and we store the, so this table we are computing and we are storing, we are not storing whole table, whole table storing is same as table lookup method. So, we do not have that much memory in our hand. So, we are just storing the start point and end point pair. So, we compute this, then we store this point and this point. So, x 1 1 comma x 1 t like this, for second x 2 1 x 2 t like this. So, x m 1, I mean there in the slide it is from 0 x m t. So, we are not storing the whole table, we are only storing the start point and end point pair, and in the sorted order of endpoint. So, that search will be faster. If you have sorted order of endpoint storing, then the search will be in the logarithm time. So, search will be faster. Okay. So, this we are doing, we store the start point and endpoint pair in the increasing order of the endpoint, so that we can do the search in a fast binary search. Okay. So, now this is the attack. So, we have stored this start point end point in the online offline phase or p computation phase, and this is the attack at the, this is called attack, or this is the online phase what we are doing. So, we are just having this start point end point pair. Now, we have so for online attack we have given a y, which is basically f of x. We do not know x, but we know the y. So, what we do, and suppose we assume y is in the table, suppose we assume this x or this k, say we say k is in the table. Suppose you have to assume this in order to working this method. Assume that the k is in the table, but we do not know where is the k, because we do not have the whole table in the online phase. We have only the start point end point pair. So, suppose say k is somewhere here, suppose this is k. Okay. So, what we do, but we do not know, this is we are not having the whole table, we are having only the start point. So, this is say start point say x L 1, this is going there, and we have endpoint x l t. Okay, so what we do? So, if this is k, then this is our y. Okay, so we know the y. So, what we do on the y, we will keep on apply f, but we do not know the position where is this k is. So, we just check y whether y is matching with the endpoints or not, that is the first check. If y is matching with one of the endpoint, then we know the previous one is the key x or k. Okay. Now, if not, we apply. So, suppose y is here, then we apply f on it and we check with the, we first check y is matching with the endpoints or not, binary search. If not, we apply f on y and we check whether this is matching with the endpoints or not. If this is matching, then y must be here, because we do not know the position of y. If it is not, again we apply f on this and we try to match. So, every time we are having the table lookup, we are matching with the endpoints. So, how many times we will do? We will do at most t times, because we know the length of the chain is t. So, we will do at most t times to, and every time we check whether it is matching with y or not. So, this is the what we are doing. Sorry. So, we have y, we are applying f, and every time we are checking, we are matching, we are doing the binary search on this to check whether this is matching or not. So, this way we will continue. Okay. Now, suppose we got a match, then we will, what we will do? Then the previous value will be the k or x, but we do not have the way to come to the previous value, but what we can do? We know there is, if it is matching with the end point, we know the corresponding start point. So, what we do? We will keep on apply the f on the start point of that corresponding row where this key is there, and then once we reach to the y, then we store the previous value as the key. So, that is the attack. Okay. So, this is the way we just keep on apply y f on y. So, until we reach to the y. So, if we reach to the y, then the previous value is the k, because we have a match over here, then we come to the corresponding start point, then we apply f until we see the y. Once we see the y, then the previous value will be the key. Okay. So, this is the attack. Now, so that to so this is the success probability of this attack is basically depends on the number of distinct key into the table divided by the key space. This is basically 2 to the power s, n is 2 to the power s. Now, so we want all the keys should be distinct in the table, but by birthday paradox we have to stop when mt into t is less than n. So, this is the matrix stopping condition. So, mt square equal to n. So, because m is the number of row, t is the number of columns. So, mt square must be n. So, this is the stopping condition. So, you have to stop this. So, if you stop this, if you keep our matrix size such that mt square equal to n, then it can cover only 1 by t of total number of key size. So, we need to have t many tables, but we need to have different function for t many tables. So, we will use some variant of this f function for t different table, where f is a simple function. This is our construction, we have chosen f to be some XOR with the from LFSR key generation, and this is basically giving us some trade off t m square. So, this we can calculate t m square, this t is the time run time, t m square is equal to n square. Now, this is the time. So, if we choose t is equal to m, so if we have time and memory is same, then we have t m square is equal to n to the power 2 by 3. So, this is the time which is very reasonable. Okay. So, this is basically, but there are some issues here, like how to handle the like false alarm. False alarm means it may happen that, so we are looking for this k. So, it may happen that there is some match over here. So, that match is creating us a match in the endpoints, but which is not basically having the giving us the key. So, these are called false alarm. But anyway, we are not going into details of those, because this is another research area one can explore. But only thing, this is a generic approach, because here we are just considering the size key space. We are not bothering about the inner design of the block cipher or stream cipher. So, this is a generic attack on. So, these are many variant, like if we have multiple data, then how we can use that. So, DP method, rainbow table, but this is out of this out of the scope of this course. So, if one has interest to explore in this area, one can, there is huge literature on this, one can have a look. Thank you.